In the previous section, we handled FPGA I/O errors. By the end of this module, you will be able to implement loop execution rate using the timing express VIs. Okay, so now we're going to start Lesson 5, Timing an FPGA VI. So the first thing we'll do is we'll kind of give a quick overview of the timing express VIs on the FPGA palette. Then we'll talk about how do you implement loop execution rates. Then we'll talk about creating delays between events, and also how to measure time between events. And lastly, we'll talk about benchmarking loop periods. So here we see the functions palette on our FPGA, and we see that within the programming palette there's a timing palette, and in there we've got a loop timer, wait, and tick count function. So the loop timer express VI, we're going to use that to implement loop rates. We're going to use the wait express VI to create delays between events, and we'll use the tick count express VI for benchmarking. So here we'll talk about implementing loop execution rates using the loop timer express VI. So the loop timer express VI, when you place it down, it's going to wait the value you specify and count between loop iterations, and that's essentially how it's going to control the period of the loop and the frequency of the loop. So the way that you would use it is you would place the loop timer express VI inside a loop. And then that way, by using this function, or the loop timer express VI, you're going to be able to perform I/O operations at a specific frequency, and you'll be able to control the loop execution rate. So we'll take a look at a block diagram to see how this actually works. So when you double-click that loop timer express VI, you get a configuration dialog. And in that configuration dialog, you're able to specify the counter units, and you're also able to specify the size of the internal counter. So let's talk about the counter units first. So one unit of that counter you can use is you can have it in units of milliseconds. You can also get it in units of microseconds, or you can also use ticks, which is clock cycles. So if you're using ticks, that's one way you can get nanosecond resolution, and we'll talk about that more later as well. The size of the internal counter, so you can select 8-bit, 16-bit, or 32-bit, but the reason why the size of the internal counter is important is that it determines the maximum time a timer can track. So to save space on the FPGA, you can use the smallest size of internal counter that you need for your application. So it's kind of a trade-off. If the size of the counter is larger, then you're going to be able to keep track of more time, but at the same time it's going to take up more space on your FPGA. So when you're choosing this, think about what's the maximum amount of time you'll need to keep track of, and then select the smallest size that can accommodate that. And we'll give examples of how these 8, 16, and 32 bits actually relate to time later on. So let's take a look at this, this block diagram, and we'll talk about and walk through how the loop timer is actually executing. So the very first iteration of this loop, we're going to get to the loop timer, and what it's going to do is it's going to record the current time as the initial time and immediately execute the code in the next frame. So the very first iteration, the loop timer doesn't take much time to execute at all. It just records the time, and then it goes to the next frame in that sequence structure and executes whatever code is in there. So let's say that code executes, and now we're going to the second iteration of that while loop. So in the second iteration of this while loop, the loop timer is going to add the count that you specify there to the initial time and wait until that count has elapsed. So if the count was like 10 milliseconds, it's going to wait until 10 milliseconds has elapsed since that loop timer was first called. So once that's happened, it's going to go on to the next frame of that sequence structure and execute the code again. So on the subsequent iterations, the loop timer is always going to be comparing how much time has elapsed based on the first time it was called. So if I put 10 milliseconds, it's going to make sure that that loop is executing at a rate of once every 10 milliseconds based on the original time of that first call. So let's talk about a caveat real quick. So what happens if the code in that second frame takes longer to execute than the specified loop rate that you've done in that loop timer? So if we take a look at this, let's say the loop timer is set for 10 milliseconds. Okay, so let's say that executes, and then we go to the next frame. In the next frame, let's say that code happens to take 15 milliseconds to execute, so it's taken longer. On the next iteration, when we get to the loop timer, it's going to notice that, the specified time that I put of 10 milliseconds has already passed, and we've run over that. Well, the loop timer is going to record a new initial time right away, and then it's going to go immediately to the next frame, and then it's going to execute code. So if for some reason in that loop, the loop timer misses its expected time, it's going to automatically record a new initial time and then start over. Okay, so in this slide we see some actual numbers that are associated with the size of that internal counter. Okay, so let's take a look at the right-hand side. Let's say we've set the units to milliseconds of our internal counter. So let's see what happens if we use an 8-bit counter. If we have an 8-bit counter, that means our counter can basically go from 1 milliseconds to 256 milliseconds. If we've gone over 256 milliseconds, then we're going to start rolling over, and our timing is no longer going to be accurate. So let's say we need our timer to go past 256 milliseconds. Well, we would need to make a bigger size for our internal counter. So let's say we increase the size to 16-bit. Well, now that counter can go from 1 millisecond to 65 seconds. If we raise that internal counter size to 32-bit, then we can go from 1 millisecond to 49 days. If I choose microseconds as my unit instead, then we see the ranges there. So for 8-bit, it goes from 1 microsecond to 256 microseconds, and at the largest size, the 32-bit, it goes from 1 microsecond to 71 minutes. So this is a good way to kind of at least get a gauge of what the size and unit, how it affects your loop rates, and when those things are going to actually roll over. So let's take a look at tick period. So if you're using units of ticks, then what that's going to represent is each tick is going to represent a clock cycle. So if you are using the default 40 megahertz FPGA clock, that 40 megahertz corresponds to a tick period of 25 nanoseconds. So if we're looking at that left column over there, each of those ticks represents 25 nanoseconds. So an 8-bit counter, if you're using ticks and a default 40 megahertz FPGA clock, it's going to range from 1 tick to 256 ticks, which if you convert that to nanoseconds, that's actually 25 nanoseconds to 256 times 25 nanoseconds. So if you need to get nanosecond resolution, you'll have to use ticks for your units. So you can see with your units, you can now have nanosecond resolution, you can have microsecond resolution, and also millisecond resolution. Now you can implement loop execution rate using the timing express VIs. Next, we will implement loop execution rate using the CompactRIO Module data rate. In the previous section, we implemented loop execution rate using the timing express VIs. By the end of this module, you will be able to implement loop execution rate using the CompactRIO Module data rate. In this section, we'll talk about CRIO module loop execution rates. So some CRIO modules have configurable timing. So if that's the case, then for these modules, you do not need to use the loop timer express VI to time the loop rate. So for example, with the NI9234 module, this is an analog input module, you can actually configure the data rate at which the 9234 module acquires and returns data. So the way that you would do this is you can do this either using a static dialog box. So you can open up a dialog box for the module properties and you can set the data rate there. And that will basically set the acquisition rate that the module will acquire data at. You could also do this programmatically using an FPGA I/O property node, and we'll talk about both of these. So in this slide, we see how to statically configure the NI9234 data rate. So if you look on the left there, we've got our project. We're going to open it up and notice that you can right-click the module 1, which is our 9234 module, and go to Properties. Once you select Properties, it'll open up a dialog for you, and within there you can statically configure some of these properties. So notice that data rate is one of these properties, and you can select it and choose what rate you want to acquire data at. So for example, here we've selected 51.2 kilosamples per second. Another way to configure the data rate is you can do this programmatically. So on this slide, you see that we can put down an FPGA I/O property node, and this is a way that we can access that data rate property. From there, we can create a constant or an input for it, and we can go ahead and select programmatically what the data rate is going to be. So in this case, we programmatically selected 51.2 kilosamples per second for our data rate. So let's go into LabVIEW and see how this looks. Okay, now we're in LabVIEW and we have a project where we have a CompactRIO FPGA target. So what we want to do here is we want to configure the data rate of our 9234. So notice our 9234 is right here. We can do this statically by right-clicking our module for the 9234 and going to Properties. So if you take a look at this, we see our module configuration. What we're interested in here is the data rate. So if you want to select a specific data rate, you would go to this drop-down menu, and then you can go ahead and select one of these data rates. Okay, so these are all the data rates that are available for the 9234. So in this case, I'm just going to keep the 51.2 kilosamples per second data rate. And I'll click OK. So if I wanted to select the data rate for my 9234 programmatically instead, I would have to use a FPGA property node. So let's take a look at that. So I'm going to create a new VI real quick. And let's go to the block diagram. So to configure this programmatically, you would right click and you want to go to the FPGA palette and place down an IO property node. So I'm going to place this down. And I'm going to move this over here and I'm going to right click it to select what module I want to get the properties of. So I'm going to go to select item. I'm going to go to FPGA target. And in this case, it looks like module 2 is our 9234. So I'm seeing that just by looking at the project. So I'm going to select module 2. And now if I left click on property here, this will give me all the different properties that are available with that particular module. So in this case, I'm going to choose data rate. And then I'm going to right click this input and create a constant. So if I choose a constant, now on my block diagram, I can programmatically set what rate I want this to execute at. So now you've seen how to set the data rate either through a property window from our Project Explorer, or you can also do it programmatically through a property node over here for an FPGA IO property node. So in this slide, let's take an example of how we would programmatically set the data rate and just what the application would typically look like. So because the NI9234 can use a data rate property to control the loop execution rate, we won't need to use the loop timer express VI. So let's take a look at this. So there in the first frame, we see that we are taking the data rate and we are setting it to 51.2 kilosamples per second. In the next frame, we are going to start the module. So in this case, the way that you would work with the 9234 module is you want to set that property, that start property, to true. The next thing you want to do is you get into the actual program where you start acquiring that data. So in this case, we have a while loop, and within that while loop, we just continuously read what's coming in at the analog input 0 channel. And once we've finished that part of the program, so once someone hits the stop button, then we go to the last part. And in the last frame, we stop the module by setting the stop property to true. One thing to keep in mind is the data rate property will set how often the module will acquire data. However, if we take a look at that while loop and we have some other code in there that takes longer to execute and makes that loop run at a slower rate, now the loop rate is actually being slowed down by the other code inside that loop. So just keep that in mind. But in this case, we don't have any other code in there, so that while loop is actually going to execute at a rate 51.2 kilosamples per second. Now you can implement loop execution rate using the CompactRIO module data rate. Next, we will describe while loop considerations on an FPGA VI. In the previous section, we implemented loop execution rate using the CompactRIO module data rate. By the end of this module, you will be able to describe while loop considerations on an FPGA VI. On this slide, let's take a look at that loop condition terminal. So if we look at the while loop here on the right, notice that the loop condition over there is a false constant that is wired to it. So in the Windows world, that looks kind of weird because usually in Windows, you'd want that while loop to stop at some point. However, when you're running an application on the FPGA, there are several FPGA applications where it does make sense just to have that while loop run as long as that FPGA is running. So just wanted to let you know that on some FPGA VIs that you see, don't be surprised if you see a false constant wired there. That just means that that while loop is going to keep running. So if you want, however, controls and application logic are still acceptable. So if you need some conditions for certain loops to stop based on a control or based on some applications logic, feel free to implement it that way as well. Okay, now let's talk about while loop iteration terminal maximum. So if we take a look at this while loop, look at the iteration terminal there. So it's the terminal that has I on it. The behavior of this terminal is once that iteration terminal gets to 2147483 that's a pretty big number, but once it reaches that value, it'll just keep outputting that same number. It's not going to roll over, it's just going to saturate at that large number. Now when you're executing code in FPGA, because of the speeds of FPGA, you might have while loops that are going to reach that 2 billion count very quickly. And then if you're relying on that iteration terminal to roll over, you're not going to get that expected behavior. So if you need that counter to roll over, then you need to implement that logic yourself. So if you take a look at the block diagram here, that's exactly what we've done. So notice that we have a shift register. We're going to initialize it with a value of 0. And then what we do is we just keep incrementing it and saving that incremented value back into the shift register. So this way, if we take a look at this particular code, it looks like that data type is a unsigned 32-bit integer. So once that count gets to that maximum value of a U32 and you add another one to it, it's going to automatically roll over to 0. So if you need a counter to roll over, just implement some logic like this instead and don't rely on that iteration terminal that you see in the while loop. Okay, so at this time, if you're able to, go ahead and do exercise 5.1. In this exercise, we're going to do some while loop timing with the R series simulated board. So in this particular VI, we're going to use the loop timer express VI to time the while loop, and that's going to be a VI that's running on the FPGA VI. So let's go ahead and open up LabVIEW and take a look at this. Okay, let's take a look at exercise 5.1, while loop timing. So in this particular exercise, we're going to add an FPGA target. And notice we've already added some FPGA I/O and renamed it to analog input and digital output. All right, so let's take a look at the VI. So this is the completed solution for this exercise. And let's take a look at some of the logic here. Okay. So the first thing we have here is we've got a while loop, and we want that while loop to execute at a certain rate. And the way that we're implementing it in this case is using the loop timer express VI. Okay, so let's go ahead and see how that was configured. I'm going to double click it. And we see that we're using units of milliseconds right here. And we're also setting the size of the internal counter to 32-bit. So depending on what your maximum value you need, you can choose the one accordingly. So in this case, we've just chosen the biggest one, 32-bit. So I'll click OK. And if we look at the rest of the code, this is where we're going to take an analog input, and we're going to take it and compare it to the limit. And then if the analog input is greater than the limit, then we're going to show it on the indicator over limit. And not only that, we're also going to output a true on the digital output line. Okay? So let's go back to our project, and we'll notice that right now, this is a simulated board, and we're able to at least simulate the execution by executing it on our dev computer. Okay, so in this case, there's no I/O actually connected because there's no board there. We're just going to, when we run it, it's going to give us simulated values for that analog input. Okay, so let's go back up here to the front panel, and let's go ahead and run it. So in this case, we're telling it, okay, we want the analog input sample time to be 500 milliseconds. Okay, so because we put 500 milliseconds here, when we go down to this code here, this is going to make our loop essentially execute once every 500 milliseconds. Okay, so let's go ahead and run this. And notice that every time the simulated analog input is greater than 0, the over limit LED will be on, and theoretically it's also outputting a true to our digital output line. The last thing I wanted to point out is notice that this while loop, when is it going to stop? Because we have a false constant wired to it, this while loop will just run indefinitely on the FPGA. All right, let's take a look at this discussion question. So if the code in the second frame of the sequence structure in that demo takes longer to execute than the value of AI sample time control, how long would each iteration of the while loop take? So think about what happens if the code is actually going to take a longer amount of time than what we set in the loop timer express VI. So this is what would happen. Each iteration of the while loop will last the same amount of time it takes to execute the code in the second frame of the sequence structure. The reason for this is because the logic in the loop takes longer to execute than the specified interval of that loop timer express VI. The loop timer express VI will return immediately and establish a new reference timestamp for subsequent calls. Now you can describe while loop considerations on an FPGA VI. Next, we will create delays between events using the wait express VI. In the previous section, we described while loop considerations on an FPGA VI. By the end of this module, you will be able to create delays between events using the wait express VI. So in this block diagram, you're able to see how you can use the wait express VI to create a delay between events. So when are some times you might need to do something like this? Well, one example is if you need to create a delay between a trigger and a subsequent output, or if you ever need to create a series of delays in your program. So for example, maybe you need to output something on your digital output, and then you need to wait a certain amount of time because of the protocol, and then after you wait that certain amount of time, maybe you change the digital outputs to something else, and then you wait a certain amount of time, and so on and so forth. So there could be many different situations where you need to create a delay between a series of events that are happening. So if we take a look at this particular block diagram, it looks like we are outputting on a digital output line, and in this case we're setting a digital line 0 and digital line 1 both to true, so we're making them into a high voltage. Then we're doing a certain defined amount of delay, and then we're going to flip digital line 0 to false, and then we're going to wait a little bit again, and then we're going to flip digital line 1 back to false as well. So this is just one example of creating delays between events. So in this slide, we see how we can configure the wait express VI. So if you were to double click that wait express VI, we would get a pretty familiar looking dialog. So the first thing you want to do here is you want to figure out, okay, what are the units you want to use for the wait? Do you want to use ticks, microseconds, or milliseconds? And then after you determine that, then you got to figure out what is the size of the internal counter. So again, the internal counter, that's going to determine what's the maximum wait that you can define for that particular function. So if you want something very big numbers, then you want to use 32-bit. If your numbers are going to be smaller, for example, between 0 and 255, then you can use 8-bit. Okay, so let's kind of compare and contrast how the loop timer express VI works and how the wait express VI works. So if we take a look at this code here, it looks pretty similar, at least the code structure does, except on the left we're using a loop timer express VI, and on the right we're using a wait express VI. So let's take a look at the loop timer one first, okay? So let's say that code in the second frame, let's just pretend it takes 25 ticks. So if that was the case, then when we run this particular VI, the very first iteration, the loop timer express VI is going to just figure out that initial timestamp and then go to the second frame immediately. That second frame, let's say it takes 25 milliseconds, and then it finishes and we go to the next iteration of that while loop. Now, as that while loop keeps executing, that while loop will execute every 50 ticks. And that's because the loop timer express VI is making sure that that while loop is executing every 50 ticks. So the loop express VI is basically trying to ensure the loop execution rate. Now let's contrast that with the right side. So on the right side, we have a wait express VI. So the wait express VI will explicitly wait 50 ticks every single time it's called. So let's walk through this, and let's again pretend that the second frame in the sequence structure is going to take 25 ticks. So if we take a look at that, the very first iteration, it's going to execute that wait express VI, which is going to take 50 ticks. And then the second frame, let's say that takes 25 ticks. So that single loop iteration is going to take about 75 ticks. So if we keep running this while loop over and over again, because that wait express VI is explicitly waiting 50 ticks each time, and that second frame is taking 25 ticks to run each time, that loop rate will actually be executing once every 75 ticks. So one way to kind of think about this is in Windows, the loop timer express VI is more like the wait until next millisecond function, and the wait express VI is more like the wait function. So that's kind of one way to think about it. Now you can create delays between events using the wait express VI. Next, we will measure time between events using the tick count express VI. In the previous section, we created delays between events using the wait express VI. By the end of this module, you will be able to measure time between events using the tick count express VI. Okay, so if you want to measure time between events, one VI that's good for that is the tick count express VI. So the tick count express VI is going to return the value of a free-running FPGA counter in the units specified. So just like the other timing VIs, you can specify the units here. So the counter units can be ticks, it can be microseconds, and it could be milliseconds. You can also specify the size of the internal counter as well. So a couple of examples of measuring time between events include if you want to, let's say you want to measure the time between edges that are coming in on a digital signal. Well, you can use the tick count express VI to see, how much time elapsed between each edge. Also, if you wanted to see how much time a section of code took to execute, you could use a tick count at the beginning and a tick count at the end, and then kind of subtract the two, and that way you would find out how much time that particular section of code took. So on this slide, we see an example of how to measure time or how much time a particular event took. So for example, we'll take a look at the block diagram, and in that first frame, we take a tick count. So we see, what that current time is. And then in the second frame, we place the LabVIEW code that we want to measure. So let's put some code in there. Let's say it runs for a certain amount of time, it finishes, and then it goes to our third frame. And in the third frame, we take another tick count and see what the value of that clock is. So afterwards, we're going to take those two tick counts, we're going to subtract them, and then we're also going to subtract one again just to account for the overhead of the actual tick count function. And then we're going to get the execution time. Now you can measure time between events using the tick count express VI. Next, we will benchmark loop periods using the tick count express VI. In the previous section, we measured time between events using the tick count express VI. By the end of this module, you will be able to benchmark loop periods using the tick count express VI. If you want to benchmark your loop periods, you can use the tick count express VI to do that. So the way that you would use it is you're essentially using the tick count express VI to calculate the time difference between each iteration of the loop. So if we take a look at that block diagram down there, notice that there's a comment there, and just imagine that in this while loop there was some code that you want to benchmark. Okay, so let's say you have some code there. What you would do to benchmark the loop period is you would add that tick count code that you see at the bottom of the loop. So notice that we have a tick count express VI that's grabbing the current tick count, and then it's going to store that in the shift register, and then on the next iteration it's going to take the old tick count and subtract it from the new one to get your loop period. The benchmarking code here executes in parallel, so it doesn't add any additional time to the loop period. Okay, and when you're done benchmarking that particular loop, what you can do is you can just remove that benchmarking code, and that way you'll save some space on your FPGA. So when you're benchmarking your loop periods, you want to make sure you watch out for rollover. So if the code that you're benchmarking is going to take more time than the maximum value the tick count can handle, then the elapsed time will end up being much lower than your expected value because of rollover. So when you're doing this, you want to make sure that you set the units, ticks, microseconds, or milliseconds, as appropriate, and also you want to make sure you set the size of your internal counter appropriately. So again, we see this table. Let's say you're trying to measure something and you're expecting that the loop period is going to be something around 35 milliseconds. Well, if millisecond resolution is good enough for you, then you can choose milliseconds to be your units, and because it's something less than 256 milliseconds, you can choose an 8-bit internal counter. But just be aware, if for some reason that loop period goes above 256 milliseconds, you're not going to get the expected result because of rollover. At this point, if you can, this would be a good time to do exercise 5.2, where you're going to use the techniques that we just talked about to benchmark a while loop period. So right now what I'm going to do is I'm going to open up the solution and walk through it with you. Okay, so let's take a look at this exercise. So right now we've got an FPGA VI thermocouple max and min benchmark right over here. And let's take a look at the block diagram. So the purpose here is we want to take some code and we want to benchmark it and see what the loop period of this while loop is going to be. So the code that we're trying to benchmark right now is we've got a FPGA I/O node and we're reading a thermocouple 0 channel. We're taking that output out, and all these calculations here, what we're trying to do is we're trying to figure out what's the maximum that was reached and what was the minimum that was reached. Okay, so just pretend that all this is some code inside the loop, and we want to benchmark the loop period for this loop. So what we do in this exercise is we add some code, and this code is already shown over here. Okay, so what we're going to do is we're going to add this tick count function, and we're also going to add a shift register. So what we're doing is we're taking the current tick count, we're subtracting it from the tick count of the previous iteration, and then that result is sent to our loop period. So our loop period is going to tell us the period, in this case in units of ticks. So if we take a look at this tick count and open it up, we notice that the counter units we've selected is ticks, and then the size of the internal counter is 32-bit. Okay. And this code here at the bottom, we're just trying to make sure that it's not the first iteration. So over here, if the iteration is not equal to 0, so it's not the very first iteration of the while loop, then we're going to go to the true case and we're going to update what the loop period is. Okay. If we go to false, so if this is the very first iteration of the while loop, then we have nothing to compare to, so we're just not going to do anything. Okay, but on all subsequent iterations, we're going to go ahead and update the loop period indicator. Okay, so let's go to our front panel. And in this case, we've already compiled it. So this is this VI when I hit run is actually going to be running on the FPGA. So let me hit run. So now it's reading the current thermocouple signal. It's showing what the maximum value was reached, and it's also showing our current minimum reached. Okay, and in addition to that, we're seeing what the loop period is. Okay, so let me hit stop. Okay, so let's take a look at this loop period. So the loop period looks like 275556 ticks. Okay, so to get that in back into units of seconds, we're going to have to do some conversion on that. Okay, so we see that the loop period is going to be ticks, and the way that we convert that into seconds is we're going to do a conversion based on the FPGA clock rate. So the default FPGA clock is going to be 40 megahertz. So to convert it from ticks based on that clock, a 40 megahertz clock is going to be 40 million ticks per second. Okay, so I'm going to take this ticks over here and divide it by 40 million. So notice that over here we've got a sample calculation. Let me go ahead and do the calculation with our current numbers. So if we take our current loop period in ticks, we've got 2755536, and we're going to divide that by 40 million. So 40 million. And if I hit equals, that gives us 0.06888 seconds. In other words, it's about 69 milliseconds. Okay, so that loop period took about 69 milliseconds. If we look at the block diagram, the thing that's going to take the most time on this particular loop is actually this analog input. So analog input is typically going to be a slow function. So if we look at the actual specifications for this module, we would see that for 9211, which is what we're using, the conversion time is about 70 milliseconds per channel. Okay, so our benchmark of about 69 milliseconds is pretty accurate. Okay, now let's take a look at the discussion questions. So in this exercise, if we configured a tick count express VI to use counter units of microseconds or milliseconds instead of ticks, would the benchmarking results in this exercise still be reasonable? What do you think? So if we were thinking about this particular exercise, the loop rate was about 69 milliseconds, right? So if we were using counter units of microseconds or milliseconds, that would still be accurate enough resolution to be reasonable. So if we use milliseconds, for example, we still would have gotten a benchmark of about 69 milliseconds. However, let's say the code that we're trying to benchmark actually executes within nanoseconds. What counter unit should you use? Should you use ticks, microseconds, or milliseconds? So if you want to measure something within nanoseconds, you're going to have to use ticks, because that's going to be the only unit that has the resolution to actually measure in nanoseconds. Benchmark loop periods using the tick count express VI. Next, we will describe data flow in FPGA.